Alright, so today we're going to talk about quantum mechanical operators and Hilbert spaces. Operators are going to be things that we can apply to our wave functions to get other things. Then Hilbert spaces are going to be how we represent our wave functions. So what exactly is an operator? Well, an operator is going to be basically anything that takes in a function and spits out another function. Now, I want to be a little bit careful when saying that because we need to know, first off, what set we're taking our functions from. So if we think of an operator as a function that's taking a function from some set A and giving you another function that's going to go to a set B, we better know what these sets are going to be. Because if I just think of any arbitrary operation that I could apply to a wave function, well, there might be operators that aren't quite valid or useful. So, for example, if we had these operators right here, so the operator x hat acting on f is going to take a function f and multiply it by x. So the set here could be just any function, any continuous or non-continuous function. So in that case, it really could be any function here for A and for B. Now, usually when we're talking about operators in quantum mechanics, well, our wave function is going to be a continuous, complex valued function, but it has to be normalizable. So we're going to have these restrictions on these functions A that we're allowed to pull from. Namely, that they have to be continuous and that they have to be normalizable. So if, for example, I define some operator I, which takes in a function, so let's say it takes in a function f, and I say it spits out the integral from negative infinity to infinity of f dx, then for any wave function, this would be a valid operator, because if it's continuous, then it's going to be integrable. So for another example of an operator, we could take the example x hat squared, which is going to take a function and multiply it by x squared. So if we applied it to the function f, we would get x squared f. And for my last example, we're going to denote I hat f as the function that is going to be the identity function. So if you give it a function f, it just gives you back the same function. Now, some of these operators are linear, and I mean that in the linear algebra type sense. So if I took x hat of f plus g, well, if we did some algebra, we'd be able to show that's the same thing as acting on acting on f with x hat, and then adding so it's going to be linear in that sense. Now, this operation from before, the x squared operator, that's not going to be linear, because if I acted on f plus g with it, I would get x hat squared of f plus x hat squared of g, but then I would also get a cross term that would be x hat, 2 times x hat squared acting on f times g. So that operator would not be linear. So now to move on to Hilbert spaces, we're going to represent our wave functions as points in something in a Hilbert space. A Hilbert space is a complex vector space. Linear algebra, when you've got a real vector space where you can add up vectors and all that nice stuff. In a Hilbert space, you have, instead of it being like a real vector space, you can multiply your vectors by complex numbers, where these vectors are going to be wave functions. And it's going to be equipped with something called an inner product that lets you do these three operations right here. So if you took, and we always denote the inner product as something like this. So if you took the conjugate of the inner product, it's the same thing as doing the inner product of y and x. And then moreover, the inner product is going to be linear in its first argument. So if you have a x1 plus b x2, that's the same thing as a inner product with x1 and y plus b inner product x2 with y. And the inner product is always going to be greater than or equal to 0. So what the inner product does is generalizes the notion of the dot product. So in normal vector spaces, we just had the regular dot product, and that does a pretty good job, but in a Hilbert space, we need something that's going to be able to work with complex valued functions, and that's exactly what the inner product does. So we just stated what the inner product has to satisfy, but what do we actually use the inner product for in quantum mechanics? Well, in quantum mechanics, our inner product is going to look like this, where we denote, we go away from kind of the math notation and denote it like this. So we always put our first function and then kind of a bar in between to separate the two, and then the second function that we want to take the inner product with. And it's going to be equal to the integral of the first function's conjugate times the second function's conjugate over all of space. So it's very important that you take the conjugate of the first argument. Don't forget that. You're always going to take the conjugate of the first argument whenever you're taking an inner product. So this gives us a nice way to represent the expectation value, because if we think about the expectation value of x, well, if we just take some state psi and act on it with x hat, then what do we get? Well, and this notation is denoting x acting on psi. Well, we would get the integral from negative infinity to infinity of psi conjugate times x times psi, and integrating with respect to dx. And what's this? Well, this is just the expectation value. So inner products also give you a nice way to define values such as those, because you could define the momentum, the expectation value for momentum and energy in very much the same way. So anytime, if you just have a general operator, so a general operator theta acting on a state, we always denote it as this, just putting the operation in the middle. So another thing that we can do with an operator, we can also take the adjoint of an operator, which we always denote as, so if the operator is theta, we always denote it as the operator and then the dagger symbol. And it's a generalization of the complex conjugate, but kind of like an operator. So it's the operations such that if you take the inner product with, let's say, psi1 and psi2 with theta dagger, it's going to be the same thing as swapping the states, but taking the conjugate of the second one. So, for a concrete example, if we want to find what the adjoint of x hat is, then we would take the integral, and here I've neglected to put negative infinity to infinity, but it's just assumed. So if we take, so the definition tells us we need to, that x dagger is going to be the same thing as acting on f with x, then taking its conjugate, and then integrating with respect to g. Well, it's multiplying it by g, then integrating with respect to x. So if we act on f, with x, we get xf, and there should be brackets here. Then we'll get x times f, and then the conjugate of that. Well, if we take the conjugate of x times f, well, x is just a real valued function, so we just have f conjugate, and then we can move that x over here. So then we have f conjugate, x acting on g. So that would mean x dagger is actually just the same thing as x. So operators that are their own adjoint are called self-adjoint or Hermitian. And these operators are going to play a really fundamental role in quantum mechanics. So we're kind of going to be bringing in all the stuff that we've learned so far. So the eigenfunctions of an operator are going to be the functions f that satisfy this relation right here. So this is really similar to eigenfunction, the eigenvalues of a matrix. Because if you recall, for a matrix, the eigenvalues are going to be the vectors, the eigenvectors, are going to be the vectors x, such that when you act on it with A, you just get the same vector, but just with a constant thrown out front. So the eigenfunctions of an operator are defined in direct analogy with that. If you act on the operator with it, you just get the same function times a constant. And it can be shown that Hermitian operators have all real eigenvalues, which that sounds like a really random statement, but what that means is if we want to represent our observables in quantum mechanics, then we should have something that's going to spit out real values, because you're not going to measure a length or a time to be negative I. They're all going to be real. So the fundamental idea is that we want observables to be represented by something that's real, which makes sense. So this is how we can state one of the postulates of quantum mechanics. So we say that the state of a system is a point in the Hilbert space. So you're going to be adding up a bunch of different functions to represent the state of your particle. And that wave function can be expanded in a basis formed by eigenfunctions of Hermitian operators. So that is a lot of words. But what it just means is that given any state that you can think of, you can build that state using the eigenfunctions of your operators. So that probably didn't make it sound much better, but as we do more concrete examples, for example, in the next video, that statement's going to make a lot more sense. So if we want to represent observables like momenta or energy, the key takeaway is that we should represent them with Hermitian operators. So to define concretely what momenta and energy are going to be in quantum mechanics, we'll take care of momenta first. Then we would consider a wave packet psi that was some constant times e to the ikx. So this just corresponds to a state of definite momenta. So if you took the derivative with respect to x of this wave packet, then partial over partial x of a times e to the ikx, well, that's just going to be ik times psi. So if we remember the de Broglie relation, that p is equal to h bar k, then we want something that when we take this spatial derivative, we should get h bar k out front. So then, if we multiply that partial over partial x, because when we took partial over partial x, we got ik out front. But if we divided by I so that I goes away and multiplied by h bar, then we're going to get something that's proportional to the momenta. Because if we do this now, if we define our momenta operator in this fashion, then whenever we act on psi with p, we get h bar over I, times partial over partial x of psi. Well, partial over partial x of psi is ik. So we have h bar over I times ik psi. Well, luckily those imaginary numbers cancel, and we get h bar k, which is just p, times psi. So this is going to be how we define the momentum operator. And correspondingly, this means that functions of this form, so that look like a e to the ikx, are going to be the eigenfunctions of the momentum operator. Because if you take a function that looks like a e to the ikx, well, then you get p times psi. So if we act on psi with p, we get a constant times psi. So that means that these wave packets, the psi is equal to ae to the ikx, are the eigenfunctions of the momentum operator. And based on our postulate that we set up here, that means we could represent our wave functions as superpositions or adding up a bunch of states of definite momenta, which is a thing that we can do. Now, what we're going to actually end up doing is representing our state using eigenfunctions of the energy operator, but we could do it with momenta just as well. So I told you that we can also define the energy operator. So since we have the momentum operator, we can pretty much build the energy / Hamiltonian operator in kind of the same way. Because the energy of a system, if we write it with respect to momentum, we get p squared over 2m plus the potential energy of the system. And so if we want to define an operator that's analogous to this, then E hat, I promise that's a hat, is going to be P hat squared over 2m plus the potential. Now, since P was equal to h bar over I of partial over partial x, the notation that we use when we say like P hat squared, we really mean applying the same operator twice. So we would get h bar squared over I squared, but that's -1. So I'll just write this to the side. P hat squared is equal to h bar squared, well, minus h bar squared. And then the second derivative with respect to x. So that means that our Hamiltonian / energy operator is going to be negative h squared over 2m, second derivative with respect to x, plus the potential. And you should really do this off to the side while you're watching, but it turns out that the momentum and the energy operator are both Hermitian, which it should be. If they're going to correspond to values that we can measure with a meter stick or a stopwatch, then they better correspond to things that spit out real eigenvalues. So next video, we're going to use these operators, the momentum energy operator, to motivate how we could come up with the Schrödinger equation. So I hope you liked the video. Let me know in the comments if you did. See you in the next video.